this. I've set up a current node, and what do I want to do for each node in the linked list that we have an instance of?
Append it to the stack.
Yep. So while current node is not equal to nil, that means we know we have a node. We can just say, hey, stack dot append, and then our current node dot value. Now we're going to get an error here. What's that error going to be?
It's an optional.
It's optional. Here's where we're going to trust ourselves, and we're going to say, well, current node was not nil. And if we look at our linked list definition, for any node that exists, there must be a value in it. So even though there's optional chaining here, we can trust that there is a value if there is a node. Otherwise, this node could not exist. So we're going to add that value to our stack. And then I'm just going to say current node is equal to current node dot next. That's how we're going to iterate through. How do we feel so far? So whenever we see a linked list and someone says like, go through it and find out stuff about it, just use this setup where you start at the head by keeping a reference to it, and then use a while loop looking to see if head is, if that reference that starts at head is nil, so this current node thing, use a while loop, and while it's not nil, do whatever step you gotta do. For us, that was just extracting the value from the node. And then the last step of that while loop, almost always, is going to be this, hey, just scoot current node to the next node. Just look one node to the right.
So I have a question. This function is more or less just giving a copy of the original linked list. It's not mutating the linked list.
Correct.
Okay.
Because it's kind of like sorted versus sort on an array. Sorted doesn't change the original array.
Mm-hmm, mm-hmm. It gives you a copy, right? Okay.
Yep.
Cool.
Cool. So right now, we haven't changed anything about our original linked list, but we do have all of its values in a stack. That's great. That means that for as many nodes as we have in our linked list, we have elements in our stack. And so that means to reverse this, we can just start taking things off the top of the stack. So how can we do that? It's going to be another while loop. I'm going to ask Phoenix, can you help me create the while loop to get everything out of my stack?
Sure.
Cool.
So what Eric and I did was we just popped the last element out of the stack. Well, we created a variable to hold the last element in the stack, and then we just popped it off.
Cool. Stack.pop last. Okay.
And then we append that to the new linked list that we created. Or I guess you weren't right.
Yeah, I got to make one of those. Sorry about that. Var new linked list is a linked list. Great. So then what did you do with that?
After it's finished, after it's finished taking everything out of the stack, you just return that new linked list.
Okay, cool. So how can we set it up to take everything out of the stack, like you say?
Well, pop last should be doing that.
Sure, but this only does it one time.
Oh, we're not in the while loop now? Oh, okay. Yeah, we have to be inside of a while loop.
Okay. So how would you set up that while loop?
While stack isn't empty.
Great. While stack is empty, except not. So while we have stuff in our stack, you went and you popped it out.
All right, and then you append that to the new linked list.
Cool. And we could forced unwrap it, but what else could we also do?
Oh, yeah.
Current last, else, return. And we can feel safe just having a return here because this function, no, hang on. How could we set this up just in case this fails?
0.
So we don't want this whole function to return 0.
You could do it if let.
Yeah, that sounds nice. If let last equal that. Why would you use an if let there, Sam?
It only runs if it's not optional.
Cool. I have to actually call this function. We'll add last in there. So while the stack is not empty, do that. And then what do we do at the end? What does this function return?
Return the linked list.
Tight. Return new linked list. Oh, sorry. Return new linked list. Nice. Interesting. I don't have a warning here. It has to do with our reference versus value types.
I progressed. They got a new name.
Let's think about what new linked list is. Is that a class or a struct? So we can change things about our class without having to actually change the object, because what's actually being changed when you have a var with a class is the reference. So if I went and said, actually, new linked list is equal to self, then I'd be changing what this var new linked list refers to. However, all I'm changing with my class here is some properties of it. When I append, it adds new nodes, but the object doesn't change its reference at all. So that can just be all a constant. How do we feel about this reversed? Is it going to get us a reversed linked list?
It should, right?
I think so. I'm just going to condense these words so we can fit it all on the page. Okay. So yeah, I think so as well. We're going to go through and remember the structure of a stack. As you add things to the stack, they get added on top of each other. So at the end of this while loop, at the end of this while loop, the value from which node is going to be available. Think about our stack. Which value will we be able to access? There's one and only one.
The last one,
And what's that called on a linked list?
tail.
Yep. Value from the tail will be at the top of our stack. Cool. That means when we go and we pop things, we can get things out in reversed order just by looking through the stack. What are some questions we have? All right. Well, the next thing we're going to do is we're going to make this conform to custom string convertible, which is a really helpful little protocol. I'm going to get a protocol stub here saying you need to add something. That something is going to be a variable called description. Cool. Eventually in here, we have to return a string. And I want the string to be in the format a node's value hyphen, I'm sorry, not hyphen, arrow, another node's value, arrow, another node's value, until we get to the tail, at which point we will not add the arrow. Do you think we can, I don't know, iterate through the linked list in a similar way? Sam, I want a description that prints out the value of each node and puts an arrow between those values except at the tail. And if I want to look through all of the nodes, what would be a good starting point?
The head.
Yep. So just like we did, I'm gonna say we got a head and what should I do? I'm gonna look until look until current node is nil to make sure I get to the end. Okay. Eric, what can I do to get there? Hi there, Eric. Sorry?
What was the question?
Yeah, what can I do in this description to make sure I'm getting current node from head all the way to the end?
While loop.
Yep.
Same before, while current node is not equal to nil, and then inside the loop, current node equal current node dot next.
Cool. So that's how we're going to iterate. And then along the way, I want to get out the value. I probably want to just, let's say, put it in a string. Our name is equal to that. What should I do in each iteration here?
Name plus equals current node but you want to,
Pen?
you want to,
No, it's a stack.
Liana froze.
Liana froze.
I think she said
oh,
interpolate.
sorry.
I want to interpolate it. Yeah, so I need this to be, current node could be any t, but I want this to be a string.
With the value.
I'm going to look at the value. Sounds good to me. So I'm adding the value. How am I going to get the arrow there?
If current node dot next is not equal to nil, add the arrow.
Yep. Name plus equals that. Cool. So here we do a little peek ahead and we say, if the current node's next, so if the thing after this is not nil, meaning if the next node is not the tail, put an arrow between us. So I'll call this a look ahead. If the next one coming up is not the tail, then do our arrow. Who could explain that back to me? Huh? Why did we do this?
Because we don't want an arrow after 4.
Want an arrow after, so which node is 4?
Yeah.
Cool. Cool. What do we do at the end of this? It's a computed property. So just like a function, it's going to need something at the end.
Return name.
Let's return name at the very end. We'll get rid of that.
Can you, for line 33, current node with the exclamation, what's going on? Or we're just forcing it? Never mind.
Yep, exactly. Cool. All right, let's test this out. Gonna get rid of some stuff here, but that is gonna be our test suite. Okay, so if I've got a new list, that's our list of arrays. So I want to make an assert right here. So if I want to set up a condition to test this on, what would the string look like for this linked list that I'm creating?
What was it? 1, 2, 3, 4.
So I'm creating in my Xcode right here a new linked list, not 1, 2, 3, 4.
Oh, sorry, I
rather
didn't see
with
that.
these elements.
So it'd be 10, arrow, 3, arrow, 10, arrow, 4. I don't think we had any spaces.
No, we didn't.
Okay.
It would probably make it prettier though, right? Cool. So if I don't see anything after I've got all this stuff, what do I know? It's kind of, yeah, so this is true. So our assert will raise an error if the condition inside of the parens comes out false. Always, always.
On the right playground, it shows it also for some reason.
It shows right here.
Yeah.
Mhm. So that's the value we got there. Let's see, maybe I'm returning something in my append. No, looks okay to me. All right. Yeah, I'm fine with it. So let's do something real quick. Let's beautify our linked list before we move on to a really exciting example of how our linked list works. Let's use some type aliases. Say I didn't want to use T anymore because T is kind of ugly. What would be, I don't know, a decent name for T?
Generic.
Yep, so T is generic. I want to use a better generic name inside of the scope of my linked list.
Element.
Where'd you get that from?
I've seen it before. I don't know.
Okay, cool. Let's make this even easier for ourselves. Let's make another type alias. And this time I want to get rid of linked list node for element. What could I call that? Yeah, let's just call it a node. And that way I don't have to put these annoying things inside. Look at what comes up while I do this. Does everyone see the toast here? What's the type of node when I use it? Capital N node.
An LL node.
Yep, with the generic type in it called what?
Element.
Yep. So node is not a new type at all. It's just the way that we're going to refer to things inside of our linked list. Cool. So what we could do is we could, throughout the rest of this, replace anytime we have linked list node with node, and replace anytime we have T with element. And I'm going to do that just so that things look a little prettier. This is just a node. That's an element being appended. Great. In this description, we don't have to worry about any of that because there's all this type inference. So line 33 has type inference. Line 31 has type inference. Line 42 has type inference. All that wonderful stuff. We don't have to indicate any types there. But line 68, I'm going to change T to be an array of elements. And then throughout the rest of this, it all seems to be pretty good. Let's go to subscript. I'm going to return an optional element. That's very nice. And just a little thing to clean things up. But what I also want to do is think about this in terms of our, what we talked about in Objective-C. We want to make sure that what the user can use, the interface, is only what we intend for them to use. So by that, I mean, let's look through our properties and methods and see, should anything be private? Should we want head to be private?
Yes, in my opinion.
Why would you say that, Aram?
Because I don't think in terms of like a public API, like we don't really need access to the head.
Yep. Yep. So this should be private because we don't want other people to have access to it. And we're writing all these fancy functions so that people can change our linked list or use it in only the way that we specify. So we don't want someone to mess up by modifying head, because we only want head to be modified by the instance methods we're creating. I'd say something similar for tail. What about count? Kevin, let me ask you, should someone be able to change the count? So should someone be able to just go and access the count of a linked list?
No, I don't think so.
Yeah, I agree. Private var count, private, because actually our instance methods are going to do the job of increasing or decreasing it. Cool. What about is empty?
I think they need to access that to
Yeah,
use
that
some of the
sounds fine.
methods.
That sounds fine to me. Cool. We could even make it public, which doesn't really change how it's going to be used, but it's explicit. I'm going to say description as well. What about append? Should people be able to append? I see Ian in the dark is nodding. You know, Ian, should someone be able to look for a reversed linked list? I'm gonna say yeah. I'm gonna say for all of our methods right now, we're setting up the way that someone uses our linked list. Ian, did you have a question?
No, I wasn't quite sure about the reversed one.
Okay. Yeah, let's just say we set this up so that someone can have a linked list, and then when they look at it, and they might be able to get back a reversed version of that linked list. Okay, cool. Subscript, we're going to let people look for elements, but if those elements don't exist, return nil. Then finally, let's come back to something we were working on last time. So if I want to have a function called remove all values, this function's job is going to be to remove all nodes that have the value input here, or the value of the value argument. Let's do it that way. So we said there are a lot of things to keep in mind. Keep in mind setting up head, setting up tail, count. So we have a pretty complex linked list here. This would actually be pretty dang easy if we just had head with no other properties, because we wouldn't have to worry about reassigning and changing the count, reassigning tail and changing the count. But let's talk about the reason we have those things. So head is a standard property. Tail, if we didn't have a tail, what would be, say there were n nodes, n number of nodes. How long would it take to find the end of the list or to add to the end of the list?
Wouldn't it take a number of times?
Yep. So it'd be O of n to get the last element in the list or to add to the end of the list. But by having tail, we can just look it up for O of 1. We can use that reference to add or look up in O of 1 time. So tail is totally not a necessary part of a linked list, but it speeds up how our linked list works. Sorry if there are barking noises outside. Similarly with count, without count, we would have to look at O of n nodes to know how many there are. Gotta count them all. With count, O of 1. Cool. So it makes it easier to access and look at things. What it does make it a little harder to do for the remove all that we're using is we have to keep track of count and tail. It actually turns out to be pretty simple because let's think about this linked list got here, and let's say linked list 1, and then linked list 2. It's going to be the one we create below. And I'm going to add something to the end. So this new list we have right here should have 5 nodes. So for the first linked list we see here, we don't have to worry about head. We don't have to worry about tail. How many nodes will be left if we remove the value 3? Yep, and be 4 nodes, and our linked list will look like this. Great. Now, what about here? We have to worry about head. We have to worry about tail. And we're removing more than 1 if we remove the value 10. How many nodes are going to be left?
2.
Yep. So there are 2 nodes, and our linked list is just going to be 3 at the head and 4 at the tail. Cool. So here's what I'm going to suggest we do. We're going to look through each node. Look through each node starting at head. That's pretty cool. And it's going to be the same while loop as before. So I'm going to say, let's grab the current head. Then let's say while current node is not equal to nil. We're going to do some stuff. Here's the thing. If the current node does not have the value, just move on. So just like we did before, current node is going to be equal to current node.next. However, if current node.value is equal to the value, here's where we got to do the stuff. We have to check if it's head, check if it's tail, reassign something, and also decrement the count. Which of these is going to be the easiest thing to do? And we're going to do it every time.
Decrement the count.
Yeah. All right. I'm gonna throw this one to you, Jocelyn. Jocelyn, how can I decrement the count? I want to decrement the count variable that I have on my linked list class. So count right here is 0, but then when we append things to our linked list, we increase it by 1. Here, I have kind of the opposite. I'm going to remove potentially a lot of nodes, but I'm going to look through each of them. So while I'm looking through each of them, for each iteration, if that node has the value I'm looking for, what should I do to the count? If the one specific node has the value I'm looking for, what should I do?
For count -1.
Yep. So count is equal to count -1.
Or
How could it?
equal, I mean, count minus equal to 1.
Perfect. So either of those is good. This is a good shorthand. So we've decremented the count. Great. And again, if it doesn't match, we don't have to do anything to the count. Now, how do we check if it's the, I'm going to say, let's check if it's the tail.
If current node dot next is equal to nil.
We could do that, yeah. Next is equal to nil. What should we do there? This is where I want to introduce maybe just one more variable. And we're going to use some wonderful Swifty stuff here. We're going to say, if this is the tail, we want to know the previous node. And here's what we're going to do. We're going to set up. Liana, would you mind muting? Thanks.
Oh, sorry.
No problem. So I'm going to set up something called a previous node. And its job is going to be just to keep track of what we saw before. Here's how it's going to work. Keeps track of the node we saw before. It starts as nil because technically there's nothing before head. But then for each iteration, just like with current node going to its next, previous node is going to be equal to the current node. So for the first iteration of linked list 2, previous is nil, current node is 10. Then when we get to the end here, previous node becomes 10 and current node becomes 3. And this is a way we can quickly back reference for the previous node in case the node we're looking at is the tail. So if we know the previous node, and we know that the current node, dot next is nil, that means this is the tail. And if the tail matches the value, we'll want to set it up so that the node previous to the tail is now the tail. How can I do that?
Tail equals previous node.
Yep. So that's all we need to do for tail, because there are only really a few scenarios here. We could be at the beginning where we need to reassign head. We could be at the end where we need to reassign tail, or we could be in the middle, which is going to have a pretty simple setup as well. Cool. Now, what are we going to do about head? Or using our two references here, how do we know when we're at head? And let's say we can't even use the triple equals.
If previous node is null.
Yep. So previous node is nil. If previous node is nil, what should we do? This is the weird one.
Head
Remember,
equals head dot next.
yep. But I don't want to, here's what I don't have a guarantee of, is that head didn't change. So using what we have in here, I'm just going to say head is equal to current node dot next. And remember, what we're doing here is we're changing the node that we're supposedly currently looking at. And so the only time that previous node is nil is when we're at the head, because it's optional. And what this is doing is, if we have this linked list, if previous node is nil, then head now is 3. So we're reassigning that. Head is equal to head dot next will also work here. But I like to use our kind of pointers, our references that we have. Okay. So we've handled the end and we've handled the beginning. What else should we do? We want to get the stuff in the middle, right? And remember that at each of these steps, what we're reassigning is a reference to a node. That's the most important part, is that in here, current node has the value, and the way that we reassign connections between nodes is reassign the reference to that node, right? So these ones are very explicit. Tail is a reference to the end. Head is a reference to the beginning. And then in between, head is beginning, tail is end, and then node.next is to reassign connections in nodes in the middle. The question here becomes, how do we reassign the nodes, the right nodes that we are looking for?
Would you reassign current node to current node.next, and then after that, reassign previous node.next to current node?
So think of it, I like that idea. What we're trying to do right here is head is now at 3. let's look at this scenario. Previous node is what?
Where are we right now? Sorry. 3.
So, yep.
It's nil.
So previous node is not nil. Now we're in the second or farther on iteration.
Oh, okay.
So let's look at this guy we have right here. So this is the remaining linked list. At the end of this statement, what I want is this linked list. Right, if we're just looking at one at a time.
Oh, so it's head right now.
Cool. Previous node is head. And current node is head.next. Current node has the same value as the one we're looking for. That's why we're inside of here. How do I set it up so that I keep the 3, but I remove the attachment to 10 and instead make it equal to, or make it point to 4?
Current node equals previous node dot next.
So current node is 10 right here. We don't even want to reassign it actually.
Previous node dot next is equal to current node dot next.
Yep. So we want to, again, this is the super important thing. We want to be rewriting the connections between our nodes. So the references for the beginning and end are really easy, head and tail. But what we want to do to eliminate 10 here is to say 3 is next. So the node we want to keep, its next is current node dot next. So we should point from 3 directly to 4. And what this also does is, well, first and foremost, it gets us what we want, the intermediate 3, 4, 10. And then it also, because there is no longer a reference to the node that was current node dot next, I'm sorry, current node holding the value 10, this node will be deallocated. Thank you to ARC. So because there are no longer any references, we literally took the reference to this node away, we reassigned it. 3 now points to 4, nothing points to 10. So 10 will be deallocated at the end of this function. How do we feel about this thus far?
We only need to deal with the count on line 176.
So yes, because let me collapse these. 176 is the last line dealing with the actual matching. So there are 3 different things that we do to remove those nodes, but regardless of which of those things that happens, at the end, we know we've removed 1 node.
Okay.
Cool. So let's see if this works.
I'm a little confused in your else statement, if you could. I just don't understand where does current node, like on line 166, how does current node get reassigned?
So that's the thing, is current node doesn't get reassigned. Current nodes here's the thing. And next is 10. Next is, so if you're like, think about next, the reason we draw it as an arrow every time is it is a reference to another node. And so current node, we are not doing anything with. Instead, we are getting the property, the next value from current node to know what to point to. So we effectively drop current node from our chain by saying, hey, previous node, don't change anything about you. Don't change anything about the next node, but instead just change what you are referring to as your next. So redraw the line that we have in this linked list so that we're no longer pointing to 10 in our chain. I think it's pretty cool.
Yeah.
It's something at each step I would recommend taking this code and printing it out. So in the end, what we end up having is actually a pretty short function because we only care if the value at the node we're looking at matches. And then there are only 3 situations to deal with: tail, head, and anywhere in between. This is the reassign something step. All right, now let's make sure it works. We've got our new list, and I want to remove all values, and let's remove 10. What should this description look like now?
Pointing to 4. That's it.
Yep. Exactly. So there's no arrow at the end. We should have successfully removed something at head, something in the middle, and something at the tail. Those are our 3 cases. Let's run it and see how wrong I am. Ready? Oh, cool. All right, seems like it worked. Let me ask, what's one thing, this is like programmer debuggy kind of thing, what's one property that we're actually not testing out in description? Let's look at description again. What is there the potential to have gone wrong after I use that remove all with description?
If it's empty?
So if it's empty, it's going to return an empty string because empty just means head is nil. And if head is nil, it won't ever enter this while loop. So we'll just return an empty string. But there are a couple properties that there is at least one property, maybe 2, that aren't being tested when we use our description. Let's see if we can debug it. It's nothing we're actually going to implement, but it's more of a like a logical puzzle.
The question was what properties we're not looking at in description?
Yeah, so like here's really something that we'd have to keep in mind when testing our linked lists. This assertion comes out true. But what our description doesn't do, it doesn't tell us if in fact the tail is in the right place and if in fact the count is correct. So these private properties, this is more of a logic problem than actually the construction of our like linked list, because it does work correctly. But remember that tail is a reference to a specific node. And so we use tail in certain places, like, where's our tail at? Well, we use tail to append, right? And if, for example, in our remove all, we didn't reassign the value of tail here, tail would point to something no longer on our list. So if we look at this line 158, the linked list that we have there, if we never reassigned the node tail, then, well, at this step right here in line 168, would be, if we looked at 4 and we got to 10 here, tail would still be this node 10. So tail would not be reassigned. The reference to the correct node would not be reassigned. And therefore, if we went to append anything to our linked list, it would be adding to some node that was no longer part of the linked list that we have all put together. I'm just trying to walk through some debugging stuff. So this does work correctly, but I say this because when I was working on it a couple days ago, I didn't remember to do this. We would be appending to a node no longer in our list if we didn't reassign the actual reference to tail. We can't just assume that tail is the last element. We have to make sure when we're changing our linked list that tail is the last element. And that's why I have this previous node. And this is all because these are references to nodes. There's nothing to take for granted. You have to make sure we explicitly say this property is for this node. And, you know, for count, maybe it's a simpler thing. We could say, let's make a public property, public var number of nodes or number of elements, which is an int, and just return count. Excuse me. The reason we do this is so that someone just has a getter. So there is only a getter with no ability to set this. Tia put an unhappy face at 12:06. Tia, are you still unhappy? Is Tia here?